Hello, this is the section 9.4 lesson. In this section you will need your calculator. In the previous section we saw a couple of tests where we were comparing two different populations. We either compared two population means or two population proportions. In this section we're going to do something similar, and that will be comparing populations, but there's a fundamental difference. In the previous sections our data had to come from independent samples, meaning that what happened to one sample had no effect on the other sample. In this section the opposite is true. To illustrate this, let's look at this first example. The actual high temperatures and the forecasted high temperatures for 5 different days are shown below. So on the first day the actual high was 80 and the forecasted high was 78. The second day the actual high was 77, the forecasted high was 75, so on and so forth. So one important point we need to make about this data is that they come in what we call matched pairs. From each of these 5 different days we got 2 numbers, the actual high temperature and the forecasted high temperature. So because these data come in matched pairs, they are not independent, meaning they are dependent. Dependent means that what happens to one of the numbers affects what happens to the other number. So for example, if the actual high temperature were a really big number, then the forecasted high would also be a really big number. Likewise, if the actual high were a really small number, then the forecasted high would also be a really small number. So this data we could not use in our previous section. In our previous section they had to be independent. Here these are not independent. Well, the question we want to try to answer is, are these predictions accurate? Well, let's just look at the numbers real quick. Notice on the 3rd and the 4th day our forecasts were perfect. In the first 2 days they were a little bit low, and on the last day it was a little bit high. But those differences really aren't too big. About half the days we were a little low, about half we were a little high, and sometimes we were right on. So one could argue that the answer is yes. So in this sample of 5 days our forecasts were accurate. Well, we want to extend that question to the larger population of all days and ask, in the population of all days, are the forecasts accurate? It appears that in this sample of days they are accurate, but in a larger population, are they accurate, yes or no? Well, to try to answer that question, let's consider this difference: the actual high temperature minus the forecasted high temperature. So for each day we would take the actual high minus the forecasted high. Well, if the predictions were accurate, then in the population about half of these differences would be positive and about half would be negative, meaning about half the time we would overestimate the actual high temperature and about half the time we would underestimate it. Well, if about half are positive and half are negative, then if we added up all those differences, the negative values would cancel out with the positive values and I'd get a sum of 0. Stated another way, if accurate, then the mean of these differences would be 0. To calculate the mean of the differences, we just add them up and divide by the number of differences. Well, if that sum is 0, then that quotient will be 0, so the mean would be 0. Yep. So to set up our claim, we're going to define the parameter, call it mu sub d, to be the mean of the population mean of the actual high temperatures minus the forecasted high temperatures. This is called mu sub d because it is a population mean. The subscript d indicates that it's the mean of a difference. So if the predictions were accurate, then mu sub d would equal 0. So that's the way we're going to state our claim. So here's the formal claim that we're going to test in words. In the population of all days, the difference between the actual high temperature and the predicted high temperature has mean 0. This is just another way of saying that the forecasts are accurate. So the claim in mathematical notation is that mu sub d equals 0. Well, if false, then mu sub d would not be equal to 0. So our null hypothesis is that mu sub d equals 0, and the alternative is that mu sub d is not equal to 0. Now, to calculate the p-value, this is a little more complicated than some of our previous tests. Let me go over the basic steps here, and then we'll go step by step in plugging this into the calculator. We're going to put our actual high temperatures in one list, and then we'll put the forecasted highs in another list, and then we'll enter this command L1 minus L2 store at L3. L3 is going to contain values of the differences. And then we're going to use a t-test to test the claim about mu sub d. So the first step there is to enter the data in the list. So we know how to do this. Go to Stat, Edit, Edit, and we'll enter our actual highs in L1 and the forecasted highs in L2. So your window should just look just like this. Now we need to calculate these differences. So we need to go back to our blank home screen. So press Quit, and then format the screen as shown. So L1 minus L2, and then the arrow L3. That arrow is read as store at. Now that arrow key you get from the STO key, which is right above the ON key. STO stands for store. So once your window is formatted like that, press Enter, and that simply takes the numbers in L1, subtracts the numbers in L2, and stores it at list L3. Now just to look at what's being done here, if you go to Stat, Edit, Edit, you can just look at those three lists, L1, L2, and L3. Notice there in L3 it's entered numbers. It's took the 80 minus 78 and got 2, 77 minus 75 and got 2, 81 minus 81 and got 0, etc. So those are sample values of those differences that we defined earlier. Okay. Now we need to do a t-test with this data in L3. So our claim is that mu sub d equals 0, or that's the alternative hypothesis, the null hypothesis, and we can do a test like that using the t-test that we talked about a few sections ago. So we need to go to Stat, Tests, choose option 2 for the t-test. Now your window, you should format your window like the figure there on the left. For input, choose Data. Typically in the past we chose Stats because we had summary statistics of our data. That's not the case here. Here we have raw data, so we're going to choose that option, Data. Mu naught is 0. Like before, that's the number that appears in the null hypothesis. Now for list, choose L3. That's the list that contains our sample values. Our next to last line there, choose the alternative hypothesis of not equal to mu naught, and then choose Calculate, hit Enter. Now your result should look like the figure there on the right. Notice it's a t-test. There you see the alternative hypothesis, mu is not equal to 0. The important number there is the p-value, 0.838. Now right below that it gives us x bar and sx. That is x bar equals 0.2. That's the mean of those differences in L3. Sx is the standard deviation of those differences in L3. Now the important number for us here is the p-value, 0.838. Now we interpret that just like we've interpreted every other p-value. We compare that to alpha. No value of alpha was given, so we'll choose 0.05. So 0.8 is definitely greater than 0.05, and so our technical conclusion is to not reject the null hypothesis. Now we'll word the final conclusion the same way that we've always done. The original claim did contain equality because it was that mu sub d equals 0. So we go to the right. We reject null hypothesis. No, we did not. So there is not sufficient evidence to warrant rejection of the claim that the differences between the actual high temp and the predicted high temp has mean 0. So we do not reject the claim of accuracy. So in other words, it appears that in the population of all days the forecasts are accurate. Now let's define some terms here. We already mentioned that our data comes in matched pairs from two different measurements. In this case, our first measurement was the actual high temperature, and the second measurement was the forecasted high temperature. Now the parameter mu sub d was the mean of that first measurement minus the second measurement. And that's always going to be the case in this type of test. We have two measurements. Mu sub d is the population mean of the first minus the second. This type of test is what we called a paired t-test. Paired because our data comes in matched pairs. T-test because we do a t-test on the mean of those differences. Now, our requirements for this type of test is, first of all, the data consist of matched pairs. That's really one of the key requirements for this type of test. That's why it's called a paired t-test. Second, both samples are random. That always has to be the case. And then third, either both sample sizes are greater than 30, or both samples come from populations having normal distributions. Now, this is a loose requirement, meaning it doesn't have to be met precisely, just as long as they're not too far from normal distribution, and the third requirement is met. So that's it for this lesson. The homework is the section 9.4.